we have already started what is called structure from motion, and structure from motion is more about reconstruction, a 3D reconstruction. Okay, just to give a quick recap, a 3D reconstruction, which means that right, you have a scene, and you have these cameras, right, which are probably looking at it from let's say, right, various viewpoints, and the idea is that right, each of these x, y, z that you have, the scene coordinate, right, you want to be able to reconstruct the scene. Okay, that's why we call it a 3D reconstruction. And the idea is you can take a camera, handheld or whatever, you can go around around a 3D object, capture multiple images of that, and use all these multiple views in order to build the scene structure. That's why it's called structure from motion, and motion refers to the camera motion, and structure refers to the scene structure, right. And this typically comes under the case where let's say certain things are not known, in the sense that right, the earlier case and all that we saw was fairly simple because we had knowledge of the baseline and all that, and therefore we could easily compute z and so on. But now we are more interested in kind of 3D reconstruction, and using, I mean, you can fix any one of these cameras as actually a reference view, and then you have to sort of, so it involves, right, motion involves the pose of each camera, which means that the R and T, right, corresponding to each camera you want, and the scene structure refers to x, y, z, right, that you want. Okay, so basically that in a sense is what is involved in structure from motion, and this is definitely harder than the stuff, right, that we have seen till now. And in the last class, I just took up a 2-view situation because that is the simplest. And today's class, hopefully, right, we will do what is called multi-view SFM. And in the 2-view SFM, you can of course initially compute the fundamental matrix. Then you can use the calibration matrices in order to arrive at what is called the essential matrix, which is a decomposition of translation and R, right, Tx into R. And in the last class, I showed that there is a way to actually decompose this. There could be multiple choices for the Tx and R, but there is one choice which gives reconstruction such that the points come in front of the camera, what is called a chirality principle. So one uses the chirality principle to sort of say which of these configurations is acceptable. There is only one configuration for which the points project on the front of the camera, or the points are in the front of the camera, and that's how we showed that you can arrive at Tx and R. And once you know Tx and R, then you can go and do a triangulation, because then a projection matrix is now available. You have the camera intrinsics, you have the R and T, therefore you can actually triangulate. And we showed last time that that given one point correspondence, right, you get 4 equations, linearly independent equations, and those you can solve using SVD in order to arrive at say x, y, z, right. Now going forward, right, we'll talk about a few more things now along the way. Now what if, let's say, the camera matrix, the intrinsics, is also not available to us, right? Then it kind of boils down to estimating your pose or the P matrix, right? Finally, when you want to do triangulation, you need the P to go back, right? That's what we showed. And the case when let's say, right, you don't have the intrinsics available to you, then one has to get a projection matrix from the fundamental matrix itself, right? Because you cannot go to the right essential, because the camera intrinsics is not with you, right? So the first thing, okay, that we will see today is deriving a projection matrix from F. Okay, so projection matrix from F, right. I am still in kind of a two view situation. Okay, in the multi-view we will see how to do what is called batch processing and so on. So projection matrix from F, right. So what we are sort of saying is that the intrinsics not available, camera intrinsics, Okay. So, in a sense, right, without loss of generality, right, what we will say is we will take the PL to be just I0, because anyway the intrinsics is not available with us, and we will take PR to be in general of the form some whatever, right, you can take it as AB. As you know, this is a 3 cross 4 matrix, and right, and this is like, and this PR is going to absorb everything, right, the intrinsics as well as you say extrinsics, right. So, this A and B will have to absorb both, and A is 3 cross 3, B is 3 cross 1, right. And there are actually, right, one can show that there is see, the more relaxed you make it, right, in the sense that the more you say that I don't have this, I don't have that, in this case, right, we are now saying that I don't have the intrinsics. The more you go down that path, then what will happen is, the good thing is that you will still want to ask whether I can solve the problem to at least to some extent, which is a good thing, but at the same time certain ambiguities will arise, right, because you are kind of leaving the thing more and more open now. So, there is not just one possible choice for A and B, okay. There are several choices, but one possible choice which is the most commonly used is this A, right, to be the A as the cross of ER, right. So, ER is the right epipole times the fundamental matrix. We are assuming that you have an 8-point algorithm or something, right, through which you are computing F, okay. So, F is this 3 cross 3, right, that we have with us, that we have computed using point correspondences, and this is of course 3 cross 3, right. This is ER expressed as a matrix, and that is a cross product form, and F is a fundamental matrix, and B itself is ER, which is 3 cross 1. Okay, one possible choice, right, is this. And why does this make sense? Right, why this makes sense is because of the fact that right now, suppose we go ahead and so let's say that let x tilde, right, as usual, let's say it's say x1, right, where this x is usual x, y, z, and okay, and then let's kind of look at say x tilde, right, which is my PL acting on the capital X tilde, and PL given that it's I0, right. So, this turns out to be x itself, right, which is x, y, z, and this x tilde dash, which is supposed to be PR acting on X tilde, but my choice of PR itself is such that, right, it is like of the form ER X F, and then I have the B, which is ER, and this I am going to multiply with X tilde, which is like X, Y, Z 1, right, and this we know can be written as ER F into X, right, plus ER, right. Now, if right, if our choice is valid, right, if our choice of A and B is valid, then what then we need to examine whether X tilde dash, what happens to this, right, X tilde dash transpose, of course, right. We want to examine what is this number equal to. So, then this will be equivalent to ER cross F X, right, let us say F X, what is this, the X tilde dash transpose, right, plus ER the whole transpose, and then F X tilde, but X tilde, right, from here is X. So, this becomes F X, right, or we can write this as ER F X. Well, yeah, one other thing, right, that we can do is we can in fact write this as actually a cross product of ER with this vector F X, right, and this whole transpose, right, is this guy, and if you multiply F X, right, then you will get F X here, plus you will get ER transpose F X, right, if you just expand it, right. And now we know that right, a cross product when you take ER with Fx and then if you take a dot product with Fx, that will be 0, right. And this one, if you watch out, right, this is nothing but F transpose ER the whole transpose times X, right. This is the same as this, and we know that F transpose ER is actually 0, right. This we have already shown, and therefore, right, it is clear that this entire thing is 0, right. Therefore, what this means is that choice of A and B, okay, that we made satisfies the kind of fundamental matrix equation, which is this x tilde dash transpose f x tilde should be equal to 0, and therefore, right, that choice is actually a valid choice. In fact, right, this is not the only choice. In general, right, I mean, in general, one can show that PR, right, in general can take this form, okay. What is like ER cross F plus ER, some V transpose, and then this can be some lambda ER, your B, okay, where lambda is some constant and V is any arbitrary 3 cross 1 vector. Okay, so in general, right, any of these choices is valid, okay, as far as PR is concerned. So the point is, right, so when you sort of so when you go from more knowledge to less knowledge of what you know about the camera, right, it makes things more and more, makes things harder, but yeah, but then it's not unwieldy, right, you can still kind of, right, do things, and all of this, right, leads to what are called structural ambiguities in the say estimation of the 3D scene. That means when you reconstruct a 3D scene, right, there can be inherent ambiguities which arise depending upon what you know, right. So you can actually classify them as two cases. One is sort of a calibrated camera case, wherein what we mean is the intrinsics are known, and then you can have another case where you say that it's uncalibrated, right. So both cases are of interest. So we will see what we mean by structural ambiguities in say SFM. Structural ambiguities in say SFM. So what this means is that, right, when you kind of reconstruct a scene, right, it does not mean that it appears the same way that it appears to your human eye, right. Just like just as with respect to homography, right, when you applied a sort of a projective transform, right, on let's say xy1 on an image coordinates, right, we saw that your parallel lines need not remain parallel depending upon, right, what kind of a transform it is, right. If it is most general, which is actually a projective homography, right, then we saw that lines remain lines, but then parallel lines, right, need not remain parallel and so on, right. So you get something like a distortion, right. You call it a distortion, right, if you want. So similar to that, right, now when you are doing a scene reconstruction, which is like xyz1, right, there it was like xy1 all image coordinates. Now looking at like xyz1 where xyz is the scene coordinate, and now you are expecting that that when you do a scene reconstruction, then that scene reconstruction can have structural ambiguity. We call it structural because it's all about that's what we mean by structure, right. You are estimating the 3D scene itself, and therefore something similar to that also happens here. So it's nothing unusual, right. We have already seen it, except that we saw it earlier in the form of a homography. It's no longer a homography, but the actions are roughly similar. The implications and the kind of things that we saw there, right, can also happen here. Okay, so that's the idea. So let's take the case 1. What is called the calibrated cameras. Again, right, I'm just looking at the, yeah. So let's let's say that we have x tilde dash, which is, let's say, PR. So calibrated, okay, PR times x tilde, right. Okay, which also means that, right, up to a scale. I mean, whenever I write this, right, a projective, we know that this is all valid up to a scale, right. So I can always put in a lambda not equal to 0 and say that, right, it is still equal to this, right. It doesn't affect anything. I mean, this we are bringing in just to bring in some notions about scaling, rotation and translation and all that. Okay, now if you know PR, right. So, let us say PR, given that this is a calibrated situation, so we know that, right, we can write this decomposed PR as KR into RT into X tilde. So, we can take actually KR to the other side, and that gives you like KR inverse X tilde dash is equal to RT X tilde. Right. Now, let us call just for ease, right, we will call this as some U tilde dash, right, that is like RT X tilde. And again, right, because only say homogeneous coordinates are involved, right, I'll multiply this with some alpha not equal to 0, and still go ahead and kind of write it like this. This I'm kind of writing for a reason. Okay. So now if you see, right, what you see is that the coordinates, right, that I mean, so sorry, this is all kind of going back to saying that based upon image data, right, what can I infer? After all, what do you have with you? Just images, right? You only images taken of a scene, that is all you have with you, and in addition, in this case, you also are assuming that the camera intrinsics are known to you. So typically in SFM it will be the same camera, okay. So you won't have like KL and KR and all. I'm just sticking to that because I'm using a 2 view, but typically it's the same camera that goes around. So there's nothing like KR, KL and all. It's 1K that goes around, but because it's a 2 view case, I thought let's just call it KL and KR, okay. But really there's nothing like KR and all. So lambda U tilde dash. So now the idea is that, right. So if you think about it, right, there is a scale factor here, and there is a rotation, right, and there is actually a translation involved there, right. So of course this comes from the camera pose, and of course there could be an alpha factor sitting there. Now you can actually effectively write this as RT, right. Nothing would change if I were to multiply it with let's say some HS, which I call HS inverse HS, which is actually a 4 cross 4 matrix, but this is let's say a similarity transform. What does that mean? So similarity transform will typically mean that, let's say you have something like, suppose I call this some R dash, okay, and then some, let's say T dash, then I have a 0 transpose and 1, some 4 cross 4, right, invertible matrix, which is a similarity transform, right. So why a similarity? Because your alpha RT, you know that when you have scale, rotation and translation, that's actually a similarity, right. That's what we saw in 2D also. So what this means is that you can actually have, I mean, right, so what this means is that, right, this remains a similarity, okay. I mean, if you actually compose HS inverse with alpha RT, right, that will still have scale, right, or this one rotation and translation. Whereas on the right hand side, right, what has happened is HS has gone and acted on actually, right, X tilde, and HS itself is actually a similarity transform. So what this means is that, right, HS can modulate X tilde in the way that it could scale it, it could rotate it, it could do a translation, whatever, right, it could do all three, and right, you will probably not see the actual X tilde. The actual X tilde is, let's say, corresponding to alpha RT in some absolute sense, but because of this ambiguity, right, there is an inherent ambiguity that I can throw in. I can say that you can have an HS inverse HS active, and still all of this is valid because image coordinates haven't changed at all. See, finally I am going back to my image coordinates, right, that's where the correspondences are. That is the only thing which tells me what I can do, and the image coordinates have not changed, right. I am still kind of looking at the same correspondence, but now the structure is not the original structure. The structure is actually kind of modified now, okay, which is what we mean by a structural ambiguity. So what it means is that in a calibrated camera, right, you can only estimate structure up to a similarity, right. That means if you see a structure, right, that looks smaller than what your actual feeling about the object is, right, it's possible, right, it can be rotated, it's possible, right, that ambiguity can come in because you cannot stop it, right. So this is like an inherent ambiguity, okay, because of the fact that all this is coming because of the fact that, right, you do not know the actual R and T, you do not know exact pose, right. See, that's why, right, structure, when you say SFM, the camera poses are unknown, See, if somebody told me what was the R and T and all, then it's all done, right? Then there's no ambiguity. But because of the fact that the camera poses are unknown, right? I'm just taking a camera, I take a picture from here, I take a picture from there, I go there, take a picture, I go there, I take a picture. I'm not recording how much I moved and all. I don't know where I am, but I want to know where I am. Right? But to what extent you can tell where you are, there is an ambiguity there, right? And that ambiguity for a calibrated camera, right? This is still a calibrated camera, even for a calibrated camera. So, right, let me just write down. So, for this calibrated camera case, the structure, the scene structure, right, can be determined up to can be determined only up to a similarity transform. In the next class, I will show you some examples, okay, just to visualize what that means. So then it automatically means that if you have an uncalibrated case, then surely, right, things should be even worse, right, which is what happens. So for an no, that is all if you knew E, essential matrix.
We did not know.
Which one?
We did not know E, right? That
Okay, no. Say that again. No. Okay, yesterday was actually a calibrated case. Okay, go ahead.
calibrated.
Yeah, for the calibrate. Okay, go on.
We know that
Hmm.
we are trying to estimate E as a product of S star. So from that we get an estimate of the rotation.
You get an estimate, but the scale, the translation is basically, right, only up to a scale.
Okay.
Right? See that R. See, the point is, right, yesterday what we showed was among those 4 choices, right, that you made, right, depending upon any one of them, right, we saw that is what brings the points in the front. But what basically, right, this is showing is that even for that choice, whatever you make, on top of that there is an ambiguity inherent. Okay, that means this HS, right, will not make the points go back or something. Okay, that won't happen. But then there is an additional ambiguity on top of the R and T, right, which we have found, because see what this means is, okay, literally, right, what this means is position, camera position and camera translation cannot be found absolutely. That's what this effectively means. Position and translation cannot be found, right, absolutely. There is always an ambiguity. This is because of the fact that we are assuming a totally sort of a totally free, hands free situation, right, in the sense that you don't have any other information. If somebody told you a little bit more, for example, if they said that there is one point in the scene whose depth I know, or for example, right, if they said something like let's say from the camera, right, if there is a sensor that tells you how much you moved, then all these issues will not come. If you just go by image data, right, if all that you have is image and then feature correspondences of the image, and based upon that, when you want to go back and say estimate a scene structure, then even the camera motion can only be found up to a certain ambiguity, because, right, that's also, as you saw, right, RT, and then you have an HS inverse coming and multiplying that. So really, right, it's not like R and T are absolute. And similarly, the scene structure is getting multiplied by another similarity transform. So basically, right, that is also not really absolute. So really, there is nothing like, you cannot measure anything in millimeters now. Right? So you cannot say that the object is 3 millimeters away or something.
You cannot say because it's not absolute.
It's not absolute, right? So all of this. So yeah, there is something more. There is something trickier than this. But I think if I say all that, right, then it'll make matters. We don't have the time for that. I'll probably pose it as a question later, okay, towards the end of the course. Or if somebody asks in the middle, right, at that time I'll answer. If somebody asks it, then we'll see. So case 2, right, uncalibrated. Because the idea is that whatever HS inverse is doing, right, HS undoes it, right, and therefore this ambiguity is there. So uncalibrated camera, right. So here, so in this case, right, you don't know KL, you don't know KR, right. So basically intrinsics not known. Therefore, right, what you have is something like this. If you rewrite the earlier situation, it will become something like PR into, you see, X tilde, right, because we can't decompose PR now. We can't write it as KR, RT and all, because we just don't know. And this PR, where will it how do we get access to PR? Who gives PR? PR comes from what I showed, right? You get the fundamental matrix, and from the fundamental matrix you can get your PR, except that there is no notion of intrinsics and all now. Correct? Yeah, intrinsics are not known. So it's kind of it's a, what do you call, you know, it has got, right, everything inside it. So what this then means is that you can have something like this, you know, let's say an H inverse H X tilde, where this is a 4 cross 4, of course invertible matrix, a projective ambiguity, a projective ambiguity. So what this now means is that, right, you can, so this is still valid, you will still get the same coordinates, but now this is of course a 4 cross 4 matrix. Now see, right, what it is doing, it's acting on, say, X tilde, right, and this is like what we saw with respect to a 2D case, right. You have like XYZ1 now, X tilde is like XYZ1, and then you have actually this one, a projective right, ambiguity, which basically means that H can take the form A dash B dash 0 transpose 1.
Still that last one can be 1.
Yeah, because I mean, right, I mean, if you kind of see the structure of PR, okay, yeah, PR is 3 cross 4, right? Yeah, in general I think, yeah, in general I think, yeah, right, H can be a full blown. H can be a full blown sort of, you know, a projective ambiguity. So what I am saying is that you cannot interpret things anymore as translations, rotations and all. See, I mean this A dash B dash, right, is the one, right, you know, which is going to change your A and B in your PR, right. So what I am saying is now there is no interpretation that this is a rotation and translation and so on. This is just a projective ambiguity, and what it can do is exactly what it did, what you know, this one, a projective homography did for the image coordinates. So whatever a projective homography did for image coordinates, something similar is going on here, but with respect to a 3D points now, right. So this X tilde is like, right, XYZ1. Right. So this XYZ1, so what this means is that now parallel lines need not remain parallel. So for example, right, if you had I mean, right, if you had two parallel lines in the original scene, right, whatever you think that's how it should have been, but then after reconstruction you find that, right, they don't seem to be parallel anymore. That is all acceptable. That's also an acceptable solution only. There is nothing wrong with it because of the ambiguous nature of the problem. Right, but that doesn't mean that, I mean, you know, it's all useless or something, right? Just that given that if you have only access to so much information, you can only do so much. The more you give me, the more I can actually improve. That's why there's something called stratified sort of, you know, a reconstruction. So what that stratified means is that a perspective, a projective, and there is also an in between ambiguity, right? I'm not kind of right, talking about. Well, actually, yeah, right. No, actually, right. This is more like, say, affine ambiguity. This is an affine ambiguity. H can be full blown. Okay, 4 cross 4. This is affine. What I wrote was affine. Okay, so there is actually a projective to affine to actually, you know, a similarity. Right, in that order you can go. Projective is the worst. Right, then followed by actually, and I say affine. Okay, yeah, right. He was right. He was asking, right, should the last one be 1? Need not be. A full blown projective need not have that, and affine has to have that, and affine will have like 0 transpose 1. Okay, because I haven't talked about what an affine model is, but an affine model is such that a projection matrix, it looks like it will be 3 cross 4, but the first 2 rows will have like P1, 1, 2, let's say P1, 4, and then P2, 1 to P2, 4. The last column will be like 0, 0, 0, 1. So the P itself will have that form. P itself will have that form, and therefore, right, that forces the H also the. So in that case, you can write it as HA inverse HA, where you want, if you want to say that it's an affine ambiguity, you can explicitly say that. So for example, right, for an affine ambiguity, right, okay, this is actually affine. Okay, so for an affine, this will become like PR HA inverse HA X, right, X tilde, which means that in an affine ambiguity, parallel lines will remain parallel. The projective is the worst. Okay, and in an affine case, this PR itself will have that structure. So the PR, right, will look like this actually: P11, P12, P13, P14, P21, P22, P23, P34, and then 0, 0, 0, 1. That is the form it takes. Okay, I mean if it's we are not talking about affine models and all. There are actually various camera models, okay, and this ambiguity and all depends upon. That's why when you say stratified reconstruction, right, what it actually means is that you can go all the, okay, let me just write that down. So what you mean is when you say stratified, right, reconstruction, so what it means is give me additional information and I can go, I'll go from a projective to affine to similarity, right. And how can I go, right? It depends upon how much information you give me, right? So if you tell that the camera model is affine, then I know that it's not, say, really a projective kind of an ambiguity. That means parallel, I mean, will still remain parallel. Like that much I can tell. But then, right? If you also give me some other information, so the information can come either from the scene, in the sense that even if you know one point in the scene for whose absolute depth you know, then you can do a lot of things. Okay, but this is assuming that you don't know, right, anything at all about the scene, or you can say something about the camera model. Like I said, in this case, if you tell me that it's an affine camera or something, then there is right, certain things which you can do. Or if you tell me motion, like for example, do you have some sensor on your camera that can tell me something about the camera motion? Any of this information can help me come from a completely full blown sort of a projective ambiguity to something simpler. Okay, I can then reconstruct my scene accordingly. Okay, is this clear? Okay, so please note that this is affine. Okay, this is an affine ambiguity. Okay, now let's kind of look at, see, multi-view, right, SFM.